Puzzles 2017.
Okay, so my name is Francisco Blas Izquierdo Riera. It's a really boring name, at least if you live in Spain. So please call me Klondike. And well, I have been working with security for 11 years by now. I started with 17. I'm a computer engineer and blah, blah, blah. That's like, you know, things that you put on the wall and you forget about them. I'm also a Gentoo hardened developer, and I really enjoy cryptography. And, well, now I'm working as a pen tester. So, well, enough about me. Now we are going to introduce you to cryptanalysis, I mean, not the internet. So let's explain what's confusion and what's diffusion. The both concepts were introduced by Claude Shannon in 1945. And you might not realize it, but they are basically the base below almost all cryptographic algorithms that are used nowadays. For example, AES is designed to have both good confusion and good diffusion, and so was this. Confusion is basically the ability that a cipher has to hide out the relationship between plain text and clear text based on the key that you are providing. And diffusion on the other side, which is what we are going to focus on, is that each single input bit that you provide to the cipher should affect each single output bit of the ciphers. Because otherwise, you can try to focus on two bits that are affected by less inputs, and then you can try to break two bits and use the information you gain from two bits in order to attack the other ones. Any questions until now? No? Well, even if you had, I could not be able to see it because there is really, really strong light coming my way. Okay, so what is the idea? We want to reproduce the cryptographic algorithm, for example, our implementation of AES or SALSA20, CHACHA20, whatever. But instead of running all the operations, we are going to try to see how the operations try to mix together the different inputs that we are providing. So therefore, we are focusing on diffusion. So how can we map the operations in order to make that to happen? Well, first, we have the concept of a black substitution box or black S box. It's an S box or substitution box on which we don't know which is the internal mapping. This is probably something that sounds familiar to people that has been doing differential cryptanalysis. So basically, we have like n bits as input and n bits as output, and we will assume that all bits of the input propagate to all bits of the outputs. So for every single output bit, we will make the union of the list of every single input bit. We also have the bitwise NOT, which is, well, totally trivial. I mean, we are just flipping every single bit. There is no cross dependency. So the output list of a NOT is the same as the input list. And or XOR, we only will interact between pairs of bits. So we just make the union of both contributor lists. Shifts are a lot more complicated if you don't have a constant on the shift parameter. So what we will do is just spread the dependencies of the first input to all the outputs, and that will be it, because we know that the first input will be in one of the possible positions spreading the bits. For additions, we can spread from LSBs to MSBs. I'm not sure if you are familiar with what we call the schoolbook addition. It's the typical algorithm that you use at the schools when you have to like add really large numbers. So you start adding the first digits that are on the right, and then you might have a carry that goes to the second digit group of digits, then you add them. So if you understand this algorithm, you can understand why we first will take the union of lists of the first two digits, and then we propagate that as carry to the second group of digits, then we propagate that contributing list to the third, and so on. Subtractions are pretty much the same, because when we are speaking of integers, we will do a complement of two, so it's a not of the operand, and we also add one at the end, so that's an addition, and then we do another addition, so we will just do the same as with addition and propagate from right to left. Multiplications, still the same, we propagate from right to left as we used to do on school. Modulos are a lot harder to map, so for now we have to use a black S box So are divisions. Fortunately, you will not see many modulos and many divisions, and most of the modulos you will see are modulos by powers of 2, which you can convert instead to an bitewise AND. And we have also a white S box, which is the standard substitution box you can find, for example, on AES. And in this case, what we can try to do is try to find out if there is some bits that don't contribute to a specific output bit. This is usually the case on S boxes like the ones that are used for Tiger, because Tiger S boxes have 256 bits of input, but they have 8 bits of input and they have 16 bits of output. So let's see if we can optimize everything. I mean, this so far is a bit confusing, but now it's hopefully going to be easier. So if we do a bitwise AND by a constant, it's really simple. We used clear alt input lists where the bit is 0, because we know that this bit is going to be 0 always. With a bitwise OR is still the same. We will clear the bits where the bits are 1. Bitwise XOR, we used copy the lists, ignoring the constant. Bitwise shifts and rotates, basically we just need to shift or rotate the inputs, which makes things a lot easier compared to our other approach. Arithmetic right shifts, we just have to move to the right and then copy the most significant bit contributor list to every single position that we have moved. Shifts and rotates of a constant are a lot harder, so for now we will just use the union of alt inputs for the second parameter. Multiplications, well, they can be replaced by shifts and additions. And as you can probably figure out, there is still a shitload of work left to do. I mean, this I started developing on April, and well, I also work full time, so I don't have that much time for this stuff. So let's go now for the cool part. I mean, if we want to attack the cipher, once we know that there is at least one output bit that has less inputs, less contributors than input bits exist on the cipher, we will just try to brute force the contributors of that single bit and try to filter out which of the combinations of contributors are actually the right ones. From a cryptographic approach, this means that you have broken the cipher because you can figure out which are the correct inputs using less than 2 to the number of input bits. In reality, of course, if we have like a bit that has 127 contributors of 128, we still cannot solve the problem, but hey, it's broken. But in other cases, when the cipher is awfully broken, you will find that maybe one bit has 1 or 2 bits that are contributing to its output, and those are the ones that are easy to attack. So, well, now is when we go for a simple demo. Yeah, now is when things start going wrong. So let's go for our 8-bit XOR. So hopefully this will work as I expect. And let's move this one here. And let's make this awfully large. So I developed a small Python library that implements most of these algorithms, which you can find along with the other talk materials. So first we need to import the implementation of the algorithms, which I'm going to do the old way. And let's see, copy and paste. So for example, here you can see that the XOR is basically the contribution of the concatenation of the lists of every single bit, and rotate is the addition, and well, it's not something especially complicated. So now we have, for example, the first cipher that we are going to implement, which is a simple XOR cipher, which you guys are probably familiar with, I hope. So as you can see, the only thing that we are doing is first we generate the lists of inputs, and here you can see that we just do the XOR of both inputs, and then we return the result of the XOR. So if we go and generate the state, and then we print the code for that state, you can see how basically we can find that bit 0 has two contributors, which are inputs 0, 0 and 1, 0. Bit 1 has two contributors that are 0, 1 and 1, 1. Bit 2 has 0, 2 and 1, 2. Bit 3 has 0, 3 and 1, 3. So by now, I mean, even if you don't know cryptography and you think that using an XOR cipher is secure, you should be able to figure out that it's not, that actually the security that that thing is providing you, it's only 2 bits for every single output bit. So let's go for something slightly more advanced so you can understand the addition algorithm. And yeah, I forgot to define the cipher. So this is the KSR cipher, which you guys are probably also familiar with. It's basically adding a constant to and now we just run the KSR cipher. So copy and paste. Okay, so as you can see here, we can see that the less significant bits, which in our case are bit number 7, only has one contributor. Well, contributions from bit 7 of inputs 0 and 1. Bit number 6 actually has contributors from bits 6 and 7 from inputs 0 and 1, and it keeps increasing as we go to the most significant bit. So in this case, if we try to approach the attack of this cipher, we would first try to break out bit number 7, and then with the results we get from bit number 7 that are considered valid inputs, we'll go to bits number 6, and then with the results from that to bit number 5, and so on. Or, well, since it's a simple addition cipher, you just try to find out which is the constant by having two plain text. But so far, I'm trying to make it simple, so you can understand what is going on. So now we are going to do for addition rotate XOR cipher with a single round. So you can see that that actually can be used with some slightly more real-world ciphers. And okay. So as you can see now, it's a lot more complicated to follow this. And when I was doing the demo with smaller screen, it was a lot easier. But oh fuck. And okay, so as you can see, basically we have a lot of contributors by the late members of the cipher. But if we go to state number 1, we can see that the number of contributors gets reduced significantly. I mean, we have some parts where we have 9, 7, 5, even 3 contributors, which are on bit number 3. So those are the bits on which we will start focusing the attack in order to continue going for the more complicated ones. And now we are going to go for, well, the real hard stuff. I mean, I have shown you how if you have one rabbit and you have another rabbit, then you have 2 rabbits. That's why 1 plus 1 is 2. That's simple addition. So now I'm going to try to show you the other one. I think you should be able to do it by now. I mean, you have learned everything you need. So in this case, I have an implementation of the first version of Petya cipher, which is the one that motivated me to start doing all this research. So as you can see, it's not very complicated. It's pretty much like salsa. Basically, we have a loop on which we will change the state number 4, which will be the Petya mix function of states 4, 0, 12 using constant number 7. And as you can see, it's basically an XOR of a cast to 16 bits, rotate of 32, cast to 32 at 16. I mean, this is pretty much hard to follow. But if you use this implementation replacing XOR 16, cast 16, etc., by the proper implementation of these primitives, you will get exactly the same results as if you run Petya, which I hope you never have to. But so, for those of you that don't know, Petya is a ransomware that runs from the boot sector, and well, it's very interesting, I guess, at least for me. So, well, as you can see here, we are not showing the list of contributors because in some cases it's awfully huge. I mean, we have like 228, 235, so it would be really hard to understand. But here we can see that, for example, for state number 14, bit number 15, we only have one contributor, and here we only have 2, 3, 5, 6, and even 7. That is actually why the original attack that used evolutionary algorithms in order to try to find the optimum solution did work, because some of the bits were so little influenced by the other bits that they were pretty much plain text. So you could use the XOR of the plain text that you already know with the result of the cipher, which was basically the key without being mixed with anything. So hopefully this can show you that, well, this kind of stuff can be used for something that is real world. I mean, I do have 2 more examples, which I think we still have some time to analyze, which is Salsa 2, which is basically 2 rounds of Salsa. So let's load Salsa 2. And let's run Salsa 2. And yeah, well, please ignore the bug that's what happens when you do presentations late at night. And anyways, you can see that not all the input bits are contributing to all of the output bits. I mean, some of them get 235 contributors, which is less than the full algorithm, whilst others get 228, which is still less than it should be. And but instead, if we pick Salsa 20, we will see that this actually does the mixing the way it should, and all of the bits have 512 bits of input. That's supposing I have not messed up the algorithm. Huh? So yeah, no, there is something that is going hopefully wrong here, and I'm not sure what it is. Yeah, I forgot to define the mixing function. Okay, so I'm sorry, this is the problem of doing a live demo, as you probably know. So, okay, so now we have the mixing function. So Salsa 2 should also work the way it should now. Yeah, so as you can see, most of the inputs only get 480 bits of contribution, which is less than the 512 bits that the state contains. And in some cases, we have almost 300 bits of contribution. I mean, of course, we cannot attack the cipher with this information, but we already know that it has flaws, and that if we use more advanced cryptanalysis techniques, we might be able to break it. In the case of Salsa 20, we will instead find that all the input bits are contributing to all the output bits, and therefore it cannot be broken easily. Yeah, as you can see, it takes a little bit more, but now you can see that all the input bits are contributing to all the output bits, because all the results that we are getting are 512. And because of that, it means that every single bit of output gets at least a teeny contribution from every single bit of input. And therefore, that means that it has a good diffusion, and it's hard to attack, at least using a diffusion-based approach. So, well, that's basically the hard demos. So now we are going to do a small comparison of both approaches. We have on one side the algebraic approach. So, well, we will try to break the cipher for all keys by finding out a simplification of the algebraic representation using additions, rotates, XORs, and we might map them to Boolean logic. Well, equational reasoning, it's quite hard. Please raise your hands if you really enjoyed the algebra courses on your high school or on your university. Yeah, I think that nobody raised the hand, so you can understand why nobody does this kind of algebraic approaches. Good. And well, simplification, at least if you want to do it with a computer, tends to be painful. It's usually an NP problem. So instead, with contribution analysis, we have something that is simpler to reason with. I mean, I think that everybody here can understand the concept of, okay, we have some inputs, we have some outputs, and we are going to see how these inputs affect the outputs. It's also successful if we have a really broken cipher. And, well, we don't care about how the contributions are made. We don't care if it's an AND, if it's an XOR. We just care about this input bit is affecting in some way this output bit. And because of that, it's really fast to run, because we only need to run the cipher, and we will only need to do M operations, where M is the number of bits that the input of the cipher has. So it has some problems, of course. It's awfully less precise than algebra, and it's also less precise than rotational cryptanalysis. If I had run, for example, Salsa 2 with a rotational cryptanalysis approach, I could have found much bigger flaws than I have found with this approach. And it will only find blatantly broken ciphers. I mean, don't expect it to find the next flaw on RC4, because it will not. It also has a lot more false negatives. That means that it will find a lot of ciphers that you will think are secure when they are not. So this should be used mostly for pen testers, by pen testers and people that is doing reverse engineering of malware, in order to try to understand which are the flaws of the ciphers they are analyzing. But if you work as a cryptanalyst at a really big government company, you cannot say, yeah, my cipher is totally secure against contributor analysis, because it most likely will not be secure against something else. So, well, that makes the presentation. There is a lot of people to thank here. My mom and dad, which are not watching this. The people that is making Recon possible, that you have over there, they really deserve a round of applause. Please, come on. And, well, there has been a lot of people that have supported me whilst I was doing this. And, well, my company actually allows me to take leave of absence. I don't get paid for doing research, but I can do research because I don't have to work whilst I'm doing research. But the most important, thanks to you for your attention. So I think we have time for one or two questions, I guess. If anybody wants to ask something, because I cannot see if you are raising your hands or anything. Let's see. Oh, now I can see. Cool.
Have you tried searching for example, you have two contributors, bit 1 and bit 2, but if you XOR them, then these are out of the contributor list. Sometimes the XOR of 2 bits doesn't affect, if you have 2 1s or 2 zeros, it's the same. They don't affect the output.
You are talking about when bits, what's it called, negate each other. For example, if I do an XOR by a specific bit and then XOR it again, true? This cannot be detected by contributor analysis. You will need to use an algebraic approach if you want to detect that, because it's really hard to follow up how the different bits are contributing to the algebraic. So what this will do is that in this case you will find bits that you think that contribute to the cipher when they don't. So that's why I said that you should use this in order to find flaws against cipher, but not in order to test that ciphers are secure. Not sure if I am explaining myself. Okay. Any other questions? I want to believe that this is because I'm really good at explaining. Otherwise, here you have a DAC that will do the explanation a lot better than I do. Not because you didn't understand a single word that I said. Anyways, yeah, as I said, I hope you are found by now. That QR code, if you want to find all the talk material and that URL. I saw somebody that was taking pictures, so please, now is the right time to take the picture, you know? Okay, so thanks a lot for your time, and, well, I hope you enjoyed the rest of the conference.